today's topic, it's predicting and preventing malfunctions, a revolutionary approach to condition-based asset performance management, APM. Okay, so this is a technical topic which will be presented to us by Dr. Nasir Hashimnia. He is actually our EIT lecturer and principal consultant at Hitachi Energy. All right, so I will let our presenter further introduce himself to you guys. So, yep, Dr. Nashir, the floor is yours.
Thank you so much for the introduction, and hello to everyone, and thank you so much for attending this technical webinar. My name is Nasa. I'm the principal consultant and power system engineer to PhD level, working with for Hitachi Energy, and also I'm the casual lecturer for the EIT. So my specialist area is in reliability and network control. So today I'm going to talk about the new approach in engineering, specifically that how we can predict and do the prognosis for understanding of failure that comes to the equipment in the network, like a power generation, utilities, distribution area, and see how we can use the machine learning and also the expert system to evaluate the condition of the asset, specifically those big assets like turbines, generators, transmission lines, and also transformers, and forecasting that when we need actually to do the maintenance and prevent any failure for these assets. So that's the main topic today I'm going to talk. Just double check with you guys, because I got to take a control from our friend. So would you see the whole screen, you guys?
Yeah, I can see it from my end.
Okay. Okay, great. So let's talk about the management maturity, asset management maturity cycle. So in industry, we have different, level of asset performance management. So the lowest level is that we run the equipment until it fails. So what does it mean? It means that we have an equipment, the cost of maintenance and also monitoring that equipment is much more than the cost of buying a new equipment. So we run it until it fails. For example, in some minings, we have some assets that, like a small transformers, like a small motor. So the cost, if you want to digitize that equipment and monitor that equipment, is much more than the actual cost of the installation and bring a new transformer or new motor in the system. And if it is fail, it doesn't affect a lot on the reliability of the whole network. So this type of maintenance, we call the reactive maintenance, which just means that you run it until it fails. But when it comes to the larger area, like a transmission and distribution, utilities, power generations, the story is completely different. So we can't run the equipment until it fails, because we have assets that they have that are very expensive, like a large turbine, which is $10 million, $20 million, large generators, $50 million, and transformers. So circuit breakers, GIS, whatever, those type of equipments are very expensive equipments. And if we lose them in the network, then there would be a huge cost for the replacement. So think about that. We have a $50 million generator. It's failed. So replacing that $50 million generator, it takes around 2 years. To be manufactured, send it back to the factory, send back to this site, and install it. So that's something that it can be tolerated. So there would be a preventative maintenance, which is based on the time-based maintenance or usage-based. So it means that in the power generation and power plant, they run the equipment for 5 years, and then there is a shutdown and they do overhaul. So sometimes over maintenance is bring a cost, or sometimes less maintenance bring the cost. So during the 5 years that they don't do any maintenance until the next shutdown is coming, there might be something is happening. for the equipment, and then the equipment might fail anytime, or the equipment is running out on a not fully loaded, and they can run it until the next shutdown within 5 years, but maybe the equipment does not need any maintenance. So it's going to be a kind of over paid maintenance, which is another cost, which is comes to the capex. So it is decided, or the best approach is that moving out from the time-based maintenance or usage-based maintenance to a next level, which is because of condition-based maintenance and forecasting-based maintenance. So it means that we run the equipment, we monitor the equipment all the time as a real-time monitoring, and then we understand that, okay, do we need a shutdown because there's something happening with the equipment, or no, we don't need to have a shutdown, so we can run the equipment. So it's going to be based on the condition of the equipment, based on the analysis of the data that we're receiving. So I narrowed down and I go through that, how we do analysis the data, what approach we take to analyze those data and make a decision based on the condition. And then at the final level, which is going through the condition-based maintenance, then we can understand that bring in the reliability center, which is bringing all the data in a model, and then we do the reliability analysis, and also then at the end we can increase or decrease the financial, and we can do the optimization. What is important in a condition-based monitoring system is that we want to improve the performance of the equipment, and also we want to increase the life of the equipment as well. So which is we're talking about the remaining useful life. So what does it mean? Now I want to narrow down in the analyzing of data. So these days we have heard a lot about the machine learning, artificial intelligence, which is can help in the power industry. How it's helping is that for the machine learning we have different algorithm, and we need some data. So those data comes from like a data which is observed data, which is inspection data, or the real-time monitoring data, which comes from the sensors. So this data comes, and then based on what type of outcome we really look for. So we are looking for the prediction of a failure. We are looking for a prediction of a kind of event, or just we want to see that what is the abnormality in the data, so we can use the different type of machine learning in the industry. So if I want to say that how the machine learning is used in industry, it can be in different area. For example, we can use it in the maintenance, which is today is the topic of predicting condition monitoring and maintenance. But however, machine learning can be also used in other type of in the other side of the industry, like in marketing. So we can do the trend trading, and also understanding the forecasting, the load variation, and we can use it in the smart grids for the development and scheduling. We can forecasting the demand response, also on the control and scheduling and dispatching. So there are different area that we can apply machine learning, because it's based on the data analysis, and we can do a prediction for the short-term prediction variation or for the long-term prediction. So our topic today is just focusing on the condition monitoring and predictive. But as I said, there's for the first part of this presentation, I just give you a bit introduction about the machine learning, and I narrow down to a solution this solution is we made it in Hitachi Energy as a group with R&D team, and then we want to present that how we can use the machine learning and data analysis plus the expert model to predict the failures for large equipment in power networks, especially utility and power generation. These days, we see that the renewable energy has been come to the market. So we are focusing on moving towards renewable energy. We're trying to increase and also the demand of the power has been increased, and then we need to increase more reliable source of energy into the system to meet the requirements of and demand of the power from the customer side. So because we really need to understand the forecasting on demand of the power, and also when we bring more renewable energy with the more components and more equipment into the system, plus that we have a main grid, which is might be a fossil fuel power, so it brings more more stress in the system. It brings more issues in the system, so which is directly affecting the performance of the equipment. And also on the other side, we have many of the assets in the system are reaching to the end of their life, so they are in the mid age or even though very close to the end of the life. But replacing of those assets because of too much demand of the power required, or doing some maintenance on them is a costing area. And then also we want to see that how we can improve the performance and increase the life of those assets. So that's a challenging that these days that we have for the maintenance and condition monitoring. So how we can overcome these challenges to the level that we have a confidence that we can extend the life, and also we can improve the performance. So we really need a kind of solution which is we can say that we can use the machine learning, even though for the forecasting of the demand. So as I said at the beginning, so when the power demand is increasing and we want to forecasting that, we can see that how much the equipment in the system goes under overloading, and which is overloading of the assets, and also because the aging of the assets also coming at the same time, so it might damaging the equipment, and it's sometimes it's unpredictable. So we want to see that how we can forecasting the failure before it happens and make our team, our crew, regardless that which area of the industry is in power generation or is in utility or in distribution area, make the crew, make the maintenance team, make the asset managers or engineers aware about that there is something is going to happen. So now narrow down to the solution. So to understand these things, forecasting the failures, forecasting that when the equipment is going to fail, we really need some data. So those data, where it is coming. So do we have the equipment digitized? Means that they have enough sensors on them to collecting the data, analyzing the data. Do we have an expert system that when the data coming is stored somewhere, and those data is based on some of the standards, or is based on well-known methods, they are analyzed properly, and also we can find out what failure is happening, or the equipment is running at the normal condition, there is nothing wrong. So what type of those data is we collecting? Are the real-time monitoring data, which is coming from the sensors, the SCADA system, historian, or PI, or is it just only observed data like inspection? Or we really need sometimes to drive a data, means that an equipment like requires some mixing of some data, correlation between some of the data to the outcome of those correlation of the data gives an indication of a failure. For example, if we have a hydrogen cooled system generator, and then we have the temperature of the hydrogen and temperature of the winding, so correlating these two data gives us a real temperature, which can be an indication of the insulation degradation on the generator, or the temperature is within a range that actually shows that the winding temperature is okay, and there is nothing bad for the insulation degradation. So how we can consider these data and modeling together to create a prediction, we have to have a solution for that. So the data is very important. We're collecting the data. How many data is available? What is the quality of the data? We need to train the data. We need to validate the data. Sometimes there is outliers in the data. Sometimes, there was a disconnection and the data has come through in a wrong. For example, a temperature must be between 50 degree or 60 degree, or the current must be between a certain range, but it has been over or below. So it might be sensors issues, it might be the collection process data issue. So such of these things is required, we should have a proper data. Is this happening? That's one part. The other part is what type of model we're using. Are we going to use a kind of machine learning or a mathematics-based model that can predict the failure when the data coming? just only for one type of failure, or is going to predict, different type of failure for an equipment. For example, if you have a generator, so we know that there would be, uh, uh, you know, different type of failure may happen. A common failure like would be like insulation degradation, overloading. It might be a rotor misalignment. It might be cooling system issue. So there would be different type of failure. So the model that we're creating based on the input data, can that model can predict, all of the failure modes, or just only it can just only shows that the equipment is going to fail or not. So it's very important that what type of model we're using, and how the model is capable to to overcome the many data coming, and based on the data categorize the data, and evaluate the failure modes. So that's something um, very important. So it comes to the way that how we using the machine learning, what model is required. So the machine learning approach needs to be applied after analyzing the power system problems. For example, if you want to use machine learning on the power system analysis side, or we want to use the machine learning for the lower level, which is the asset level. So that would be a complete different algorithm which is used. So because the outcome that we need for the power system is more on the frequency variation, more on the voltage variation, and also on the power demands. When it comes to the lower level, which is the assets, like generators, motors, any type of assets. So we're mostly focusing on the performance of the asset, and also the remaining useful life of the asset, and the failure modes of the asset. So there would be different type of machine learning that we can use, but at the end, all of them requires a proper data, which is if there is no data, then the algorithm doesn't work. So whatever comes must be clean, must be trained, must be evaluated, and that algorithm which is used, it gives you the outcome. So if wrong data coming, wrong output is coming out. So as I said, it's very important that what type of algorithm we're using, for which purpose, and what data is coming. And if our purpose is something that we want to go through the failure modes, we have to understand that that algorithm is capable to collect the data and analyze this data, and give us a confidence about the algorithm. So in the classification of machine learning, we have different type, like a supervised, unsupervised, semi-supervised, and reinforcement learning. So I can't go through the details of these because it's a huge topic and it's required, lots of study. But you can see that there would be different algorithm. Like when we're talking about supervised learning, means that we can use the linear regression, decision tree, and neural network. So there would be different type of algorithm. But how we're using this algorithm, and what is the purpose that we want, this is something requires lots of study. But because of the time, let me show you the actual solution that we have created, and we think that it's sorted out most of the issues with the equipment, and creates a proper and confidence output. So what you see here, there is a chart that you can see. For example, we have a condition monitoring. Now I've narrowed down my presentation to a level on the asset level. Think about that. We have a power generation, or a transmission or distribution side, or a specific equipment. So now we have a condition monitoring now on the equipment. So the condition monitoring, collecting the data. So those data comes as a real-time data. Like it might be a different type of data. It might be a electrical data parameter like a frequency, voltage, power factor, or it might be a mechanical data like a vibration, pressure, flow, this sort of data. So it comes as a real-time data up to 2 days. So we're collecting this data, and sometimes we have an expert model to analyze this data. For example, if the temperature goes over a certain amount of temperature or threshold, there would be an alarming, and then there might be something wrong with the equipment. But however, that condition monitoring is up to today, means that we can analyze the data and find out what's wrong with the equipment up to today. But however, because we have lots of demand and we can't shut down the equipment if there is something wrong with the equipment at this stage. We want to see that if we can run the equipment for the future. So with with this real data coming, how we can predict the failure, for example, for the next 3 months, 6 months, 1 year, up to 3 years. And if we run our equipment on a full load, how much would be the percentage of failure uh, happening in the next 6 months? So I'm talking about the future. Future means the prognosis. Future means the forecasting. Forecasting a failure mode for equipment based on the input data, based on the real-time monitoring data. So what I want to say here is the prognosis modeling, which is we're using machine learning and expert model, can support the condition monitoring on top of that. So the condition monitoring is required because we can understand the condition of the equipment at this stage. But however, I need to know what's going to, how much the percentage, how much would be the probability of failure for the equipment in the next 6 months, 1 year, and what would be the percentage if it is the failure modes, for example, is going to increase to 50%. So then I have to make myself ready for a failure before it happened. So I have an indication that what's going on in the future. For example, if I want to make an example in real life. So if you want to do the camping, for example, next 2 weeks, you go on Google and look at the you look at the environment, and you can Google shows you the for example, in next 2 weeks, we are going to have a a sunny day, or the day that you want to go for the camping. Um, um, there might be a rainy day, so you make yourself ready for that camping. So you take some jackets with yourself. The weather is low. The weather is the temperature is high, low, and many other information. It's forecasting. So again, here prognosis modeling also is the same. So it's forecasting a failure that might happen, and you as asset owner or reliability engineer or engineers make yourself ready for that. If you need to bring a component, if you need to make a shutdown, if you need to buy a certain component or equipment to fix that issue, then it's something that helps you forecasting how many crew you need, and also how much money you need to spend for that one. So that helps for different level engineers that who directly working with the equipment, engineers that or reliable engineers that forecasting the cost, and also the asset managers, they look at high level for capex, and also the maintenance cost, and also the opex that they need to buy a new equipment, for example, or not. So that's the whole strategy about that, how we do the prognosis modeling and diagnostic. What the other important thing is that if you want to do the prognosis, also if we can see that, okay, our equipment running at the 100% load, and we can see that there is something wrong is happening, and we can forecast the failure mode in the future, increasing with the load of 100%, and we see that the probability of failures has been increased to 60% or 70%. There must be an option that if we're reducing the load from 100% to 80%, then we have to is there any possibility to forecasting the failure most, the probability of failure is going to be decreased or not, from 60%, for example, to 40% or not? And if we reduce that 20% probability of failure, can we run the equipment until the next shutdown? That's something that required data and a proper modeling, which can help to understand with the load variation on the equipment how much we can reduce the probability of failure on that equipment. So let's go through different assets and different methods. So in a normal industry at the moment, we have expert models, which is a well-known models. For example, for transformers, we use dual triangles, IEEE standards. For the gas turbines, definitely there would be different type, hydro turbines, any other equipments, until it comes over here, which is we we're thinking that, sometimes we need to combine the expert model and the data analysis and mathematics all together to forecast and also forecast the probability of failure and also improving the performance of the equipment and calculating remaining useful life of the equipment. So machine learning purely it is great, but just only if you want to focus on data only, it doesn't work well, specifically when we have a very complex um, um, uh, model and complex, network. So even though we have different type of algorithm, as I showed you at the beginning, but even though these models can be applied for different component types, the limitation is that they can only predict a single future parameter value or a component state. It just shows that the temperature is going to increase, just that's it, or it might just say that there might be the equipment fail or not. So that's good, great, but it is not something that we can use it properly. We want to understand what of the failure modes, how many failure modes may happen, how many malfunction may happen for that equipment. So in this situation, we think that we have created a model which is based on the statistics process, which is based on the using Markov chain and also the Bayesian rules. So the Markov chain is a very high sophisticated mathematics approach that the data coming, it doesn't matter what type of data is a data type, is a temperature, it's a voltage, it's a frequency, what type of data. So the Markov chain supporting to predict the variation of the data. So for example, we have an equipment here. So the equipment is digitized with the different sensors. The data is collected from different part of the equipment. It comes to the model, which is based on the Markov chain. So the Markov chain is calculating and trending the data for the future. So the data comes up to today, and then the Markov chain trending that data based on the history of the variation in the data. And after that, we can use the Bayesian rules. So Bayesian rules is based on calculating the probability of failure. So we have different type of data coming for detecting a failure mode. For example, the insulation degradation or short circuit for the winding of the generator. We need the temperature on the three phase, we need the current, and also we need for example, the ambient temperature. So these are the minimum three set of data which comes to the Markov chain. Markov chains based on the history of the data can predict the future trending, and then this all comes together and Bayesian rules calculate the probability of failure. So it says that there would be a chance of up to, for example, 50%, 60%, 80% chance of short circuit happening for this generator because of this variation in this data and trending. And based on that, we can also calculate the remaining useful life of the equipment. So the probability of failure, the remaining useful life. So you can see this flow chart. So firstly, the future probability of distribution of parameters given its current, which is Markov chain, and then and secondly, the probability of malfunctions given the current value of the parameter based on its condition probability given the parameter, allows a simple general approach for determining the malfunctions of a technical component, which is the Bayesian rules altogether. This is the whole solution that we have created, and based on that, we can calculate the probability of failure for the equipment. So these are the algorithm breakdown, which is I don't go through that because required lots of time. So let's move on. And what is the important part of this is that how we can calculate the remaining useful life of the equipment. So the remaining useful life is it is based on the probability of failure. So if the probability of failure increasing, the remaining useful life of the equipment changing. But however, we think that the probability of failure increasing. So on the other side, remaining useful life is decreasing. If we improve based on the prognosis that we're doing, if we change the load on the equipment, or if we do some maintenance of the equipment, so we can reduce the probability of failure, and then we can increase the reliability, the remaining useful life of the equipment as well at the same time. So that's something that, the algorithm that we have created and the mathematics that we're using can give us a prediction of the remaining useful life of equipment. For example, for a transformer, for the equipment that they have insulation, if we can predict the failure for the insulation, we can predict also the remaining useful life of equipment, because we know that if the insulation degradation happening or insulation problem happening for a generator or a transformer or a cable, it means that the equipment is gone, regardless that the other part of the equipment, like rotors or bearings, these bearings or rotors can be fixed later, but the insulation is something that you have to send it back to the factory and rewind it. That's a huge cost. That's something that and also the other things that insulation degradation happening, there might be a chance of failure when the transient voltage is happening or a spike in the current is happening. So that's something that it might happen because the insulation has already degraded. So if we have an indication that the insulation degradation is going to happen, we can predict that there might be a chance of failure, short circuit happening for the for the winding. And also we can also predict and calculate the remaining useful life of the equipment as well. So to do this, applying this solution into the for each equipment, we really need to understand that how the process is working. So if you have a power generation, steam turbine or generator to a gas turbine connected to a generator, and generator is connected to the bus bar, and bus bar is for a transformer. So this complex model, first of all, we're starting with the single line diagram to understand how this model is working. Then we need to understand what data is coming. Sometimes, as I said at the beginning, the data comes in a very bad mood, means that there would be so many outliers, there would be so many bad data into that, which is may affect the performance of the model. So the data cleaning, data analysis is required. So we have to understand that the normal data, there must be a threshold with the data. So if we're talking about the current, it must be between this amount amps or to this amount amps. So if it goes over, it might be an alarming, or if it's very high, or that might be an outlier, or for the temperature as well. So this data, which is coming from different part of the equipment and from different part of the plant, so it's required to be cleaned properly. These are the big data, but all of them must be cleaned properly. So when it is cleaned properly, then it goes to the model. So you can see, for example, this is an example. We have a data coming, then this data, we set some threshold for this data because we want to understand that where would be the normal data, where there is an abnormality in the data as well. And it is required for forecasting because, as I said, Markov chain is look at the variation of the data, calculate that, see if there is a huge variation or less small variation, and then it's going to predict how much would be the trend of the data. Is going to increase that in the future, or is going to decrease in the future. So that's something that the clean data, we have to give a meaning to data. Data must be meaningful for the calculation and also for the model. So if the data have a meaningful data or not a meaningful data, and they are not a clean data, then the model doesn't work well. And the other thing that we have to make sure that data are correlated with the components. So for example, if it's a temperature, where it is coming, which part of the equipment coming, because our model is based on failure modes. So if you have 10 different failure modes happening for an equipment, for each of them, what data is required from where part of the equipment. So that's another part that which is because of feature engineering, which is we evaluating the common failure modes, what data is required, and then also this data must be within which type of thresholds, what would be the range, the normal range, abnormality, and very high abnormal situation, because all of them is required because Markov chain is going to calculate based on those data variation. So now I explained about the solution, how the solution work, what the data requires, how we can predict the future probability of failure. Now it is important to use it in industry like a wind farm. So think about that. We have a wind farm, offshore wind farm, installed, in a very rural area and in the middle of the ocean, for example. So if the failure is happening for any of these turbine, then we need to send the crew to this to over the ocean and then try to fix them. It's a very time consuming and very costly uh, activity. But however, if we can apply data, machine learning, and mathematics approach, and we have a model, and the data is coming, we can predict the failure of which of those turbines is going to fail and from where. So if we go narrow down in the detail of their turbine, out of the 100, for example, we have 100 turbines. Now let's narrow down into the a turbine. So we can see in the nacelles we have the blades, we have a main rotors, we have a gearbox, there is a generator, and then the cables, and then it comes to transformers as well. So we can see there are different components inside the nacelles. So, and also you can see there are some data coming out. So data is from different sensors, which is on the different part of the equipment. So this data is collected, comes to us to an area, to a cloud base or any area like a SCADA system. Then back and then it comes to the model. So the data is cleaned, comes to the model, and the model starts calculating the probability of failure. For each of these equipment, there will be different failure modes. For example, we might have 5-6 different failure modes for the generator, 5-6 different modes for the main turbine, main rotor, or gearbox. So I, as an asset owner, I, the person that I'm the reliable engineer, when this data coming and then I can predict, what type of failure is happening. So then I can order and raise a ticket for maintenance for the specific turbine within the wind farms, and also which part of the equipment required, which part of the turbine requires the maintenance. So that's something that we really need to have it in industry to narrow down, to decrease the cost and maintenance, and also make it based on the condition monitoring. So this is an example here for the generator. On the left side, if you can see it, there are some different failure modes and then different parameters correlated to the failure modes. So these parameters are clean, goes to the Markov chain, and Markov chain is start calculating and predicting the trend of this data, and then the Bayesian rules is going to predict the failure modes, for example, for each predict the probability of failure for each of these failures that may happen for the generator, which is inside the turbine. So this is one of the examples that we applied this models long time back for a wind farm, for example. In 2020, 19, 20 December's, everything was perfect. The data came through, and there was a probability of failure calculation, and it was okay. So there might be a large chance of 1%, 2%. But on 24th of December, the calculation 4 days after the calculation shows that there might be something is going to happen in January 2020. So we were on 24th of December 2019, but the prognosis modeling shows that something may happen in January or end of January 2020. So that was an increase. So it means that from 24th of December, there might be a chance of increasing the probability of failure, and it's going to be increased in a higher level in 2024. And then 4 days before the failure happened, the prognosis indicates on the 24th of June 2020, something happened and failed. So it shows that we could predict the failure 6 months before, and eventually it was it shows that it's going to happen, and we present it to the asset owner. But because we wanted to validate this model, they wait and they found that, yeah, in 2020, 6 months after, it happened. So you can see that with this model, analyzing the data, putting the data into the model, we could manage, to find out, where the problem is going to happen. So that's a good achievement, because actually the asset owners could find out, what's when it's going to happen, and make themselves ready for that. The other thing is that the model also can help and see that if we can reducing the load on the equipment, can we run it longer until that we have a shutdown or not. So that's another thing, that the next level of prognosis should have it, which is reducing the load or increasing the load, how it's going to affect the probability of failure. On top of that, for example, we have a transformer also in the turbines. That's a very important component, because we're transferring the power when the generator transferring the producing the voltage and the power. So we need to transfer it. So for that one, again, the power transformers may fail, but however, we need to analyze the data as well. So from the data coming from different part of the transformer, this one is a power transformer, but actually the transformer is used in the turbine is a smaller transformer. But however, the data which is coming from the oil quality, from the DGA monitoring system, from the DGA analysis, and also the voltage and the current, also can be used in the model, and when we can predict the failure for the turbine, for the transformer. But most of the the failure that may happen for the transformers in the wind turbines are the insulation degradation, because of the humidity from the ocean, because of the salt and the leaks happening, corrosion. So the insulation inside the transformers may fail, or degradation is starting, so they put the transformers on the failure of short circuit, or there might be a mechanical stress on the winding, or voltage transition is happening, then the transformers may fail. Replacing that transformer specifically specifically for the wind turbines when it's offshore, then that's a huge cost. So, but if we predict based on the data analysis, if you have a trend of these DGA analysis, dissolved gases and oil quality, we can trend and find out when the insulation is going to fail, or if the transformers is under failure or not. So even though if we can monitor, if we can do bringing the expert model, means that the transformers can be analyzed by dual triangles, well-known methods like pentagons or dual triangles ratio. The output of this analysis can be as an input into the model. For example, in this situation, we can say that the data is coming directly to these pentagons or dual triangles. Dual triangles shows that there is for example, demo problem. So if that demo problem is calculated every day, then it's going to be an input to the model, and based on doing some percentage and calculation on derivative parameters that we can apply as an input to the model, we can find out that the severity of this demo problem is going to go to the next level or not, and when we need to do a shutdown and take the transformers out. So that's another beauty of the solution, that can predict the insulation degradation. So this is an example that we could manage to find out, what would be the insulation degradation happening for that transformer, based on the ratio of the carbon monoxide, carbon dioxide, and also other gases generated for the next 5 years, and also the remaining useful life of the insulation, if it's going to happen. For example, for the next 12 weeks, which is 3 months, the remaining useful life was around 60%, 80%. But when it comes to the 5 years, you can see that it's going to be decreased a lot. And also the turbine, the gearbox side as well. Again, this is another component which is we can find out. For example, for that turbine, you could see that the data has changed and moved to the dangerous zone. I don't want to say it's a very dangerous zone, but you can see that there is a trend that at that point, the trend that Markov chain has calculated, and for the future, you can see that there is a huge, there would be a change increasing because the history shows that the temperature has been or vibration has been increased and has been the high level for a long period of a time. So that and then you can even bring it into the model, you can see that's red. Red means that the percentage, the probability of failure has been increased for long, for more than 50%. But it's not going to happen today. It's going to happen for the next 6 months or 1 year. So we know that there would be a kind of failure happening for that turbine in the future. So as a summary of this part of this presentation, I can say that we want to do the prognosis, completing our condition monitoring. But how we do that prognosis, there would be some if questions: when the condition going to be changed, when the condition equipment going to be critical, when we get a warning and alarming. These are talking about the future. It hasn't come to, but we have to have an indication that when would be the critical situation for the equipment. When would be the best time based on the probability of failure to fix the equipment? When we need to the schedule. These are the future, which is we don't know. We have to have an indication for that. And will other plants in the fleet have the same issues or not? So that's again in this comparison between the probability of failure for these. If you have a multiple plants, and we want to see, we want to do the comparison. So the future of the industry is using, if you have more data, if you have more data, and if you have a proper modeling, we can improve the performance of the plant. We can improve the performance of we can increase the efficiency. We can improve the performance of the equipment, and also we can increase the life of the equipment based on collecting the data and have a proper modeling. Thank you, and I'm happy to hear if there's any questions here.
Right. Thank you so much, Dr. Nasiri. It was a very informative presentation. Thank you so much for that. So now we can actually proceed to our
Any question?
Yep. So
Yeah,
yeah, just to
you
let
go ahead, please.
everyone know. So yep, I'll take it here. So yeah, for those who are interested, so what are the courses that covers this topic? So basically, that is as you can see on your screen. So we have the 52911 WA Graduate Certificate of Internet of Things for Engineering. We also have the 52886 WA Advanced Diploma of Industrial Automation Engineering. We also have the 52872 WA Advanced Diploma of Robotics and Mechatronics Engineering. We also have the online bachelor's degree, Bachelor of Science in Industrial Automation, and online Masters for Industrial Automation. All right. So these are the courses. We have a range of courses under Industrial Automation, which are upcoming. So we have intakes for the September. So as you can see on your screen, these are the courses under Industrial Automation Engineering that has upcoming intakes. All right. So first one for September is the Advanced Diploma of Electrical and Instrumentation E&I Engineering in Mining. All right. And we also have September 10, Professional Certificate of Competency in Instrumentation, Automation, and Process Control. And on September, same with September 10, that would be on Allen Bradley Contrologics and PLC platforms. Okay, that was for September. All right, now let's proceed with our short Q&A, Doc. We have a few questions here under the Q&A. Okay, so we have one here, Doc, from Napoleon Kisumbing. So he was actually asking, Doc, can you integrate the machine learning prognostic model into the SCADA system for power system?
Yeah, we can, as I said at the beginning, we have to first of all understand that what we need to do for power system. Are we going to forecasting a demand? Are we going to
mhm,
forecasting a variation of the frequency, or what is the purpose of applying the machine learning in the power system? If we understand that first, then we can find out what type of machine learning we can apply and what would be the output. So that's very important at the beginning. What is the purpose? What is our target to using
mhm,
the machine learning in
mhm,
power system?
mhm,
Yes, definitely. If our target is on the system level, or our target is on the equipment level, then there would be different of algorithms can be used. Are we going to use the prediction of the failure for the short term? Are we going to predict the failure for the long term? Or in the system level, are we going to forecasting a demand power variation? So that would be different type that we need to do a study. That's a huge topic,
mhm,
and require lots of study before applying a proper machine learning to the purpose that we are looking for.
mhm. Thank you so much, Doc. Hopefully, Napoleon, it answers your question. So we have the second one from Andrew Hewitt. So he was actually asking, Doc, do you need data from when the plant is first commissioned, so that you have a fully history of the plant's operation?
Yeah, so that's a good question. Definitely, um, the history of the data is required, because we understand that how was the equipment was run the last two
Mm-hmm,
years, 1 year,
mm-hmm,
and then what is the condition of the equipment at this stage. So then the solution, which is a Markov chain, as I said, look at the trend of
mm-hmm,
the data and then predict the future trending of the data. The history of the data is required. So it means that at least if you have a 6 months
mm-hmm,
data with a high frequency, the trending can be easier. However, sometimes there is no data available, or just started to collecting the data, then we need to wait, at least for 2, 3 weeks, 1 year, to accumulate some enough data, and then start, calculating the trend of the data in the future. I hope that I responded to your question clearly.
mm-hmm. Yep. Hopefully, it answers your question, Andrew. So we have another one from still Napoleon Kisumbing from Midnert. Can you cite a particular machine learning software have you used in predicting and preventing a malfunction or failure in electrical power system? So he was asking about a particular machine learning software. No.
Um, there are different type of software is used. You can use MATLAB, you can use the Python. There would be different type uh, that's you can use. There are so many
Mm-hmm,
open sources, but as I said at the beginning, the purpose of using machine learning, why we want to use it in a power system.
mm-hmm,
Definitely, this is the first step. Using the tools, there are so many tools in the industry you can use. Tools, it doesn't matter. First of all,
mm-hmm,
understand that why you need machine learning, why we are applying this, what is the purpose. As I said, it's a condition monitoring. Is it using for asset management, or is it using for the forecasting? Is it using for
mm-hmm,
trading energy? Where we want to use it. So then that would be the first step.
mm. Thanks, Doc. So, yep, hopefully it answers your question again, Napoleon. So, all right, we have another one. It's a very interesting one. Okay, is all data passive data measured from sensors with a plant operating under normal operating conditions, or are these cases where additional test data may be required, such as injecting a test signal?
So yes, good question here. Is that machine learning
Yep.
is required high frequency data range. Yeah, sometimes, as I said, those data is directly coming from the sensors, from the SCADA in a high frequency range. And
Mm-hmm.
sometimes, uh, there must be an electrical test or some testing that you did with the
Mm-hmm.
low frequency data. But um, the solution that I provided here is based on the high frequency data. So um,
Mm-hmm.
injecting that, for example, a test data with a low frequency, it might be useful as a look at a trend. But actually, the algorithm operating based on the high frequency data, which is coming from the sensors or SCADA system or Historian Pi. So I want to say the nature of machine learning is based on the high frequency data.
Mm. All right. Thank you so much, Doc. Hopefully it answers your question. What's that? Oh, it's Andrew. Okay. Thank you for that
Andrew, yep.
question, Andrew. Andrew has a lot of questions as well as Napoleon, so that's good. So
That's
yeah, one last question before we wrap up, Doc. This is from the chat. I cannot see his name, but he was actually how to address restore asset health in simple term.
how we address what? Sorry, I
How
didn't
to
get the
address,
question.
yeah, he said how to address restore asset health in simple term. Is this somehow related to?
So there are so many methods at the moment,
Mm-hmm,
in an industry that they can use with the observe and measure parameter coming from
mm-hmm,
the equipment, like high frequency data and also testing data,
mm-hmm,
and you can calculate the health index. That's a simple way. There are so many. For example,
mm-hmm,
one of them, I want to say there is a framework for the health index calculation. One of them is a
mm-hmm,
DNO, distribution network operation, from the British network. Okay,
mm-hmm,
distribution and transmission network. They have created a framework for health index calculation, probability of failure calculation. This is just only a basic mathematics approach. This is a simple way of calculating the health
mm-hmm,
index. But if you want to go in the higher level, in a very
mm-hmm,
more advanced, then the simple health index doesn't help, because it's just only a simple calculation. But I recommend you search on the Google and search for the DNO, distribution network operation
mm-hmm,
framework. You can, I think it's open source. You can download it and you can go through that and see that how
mm-hmm,
the health index is calculated, the probability of failure is calculated based on the observed and measured
mm-hmm.
parameters that you collect from your assets or from the OEM.
I see. All right, thank you so much, Doc. All right, thank you so
Thank you,
much. So
everyone.
yeah, I think that's actually for the Q&A session. So for everyone who was actually asking, so this is actually how to get your certificate of attendance. So you need to scan the QR code here or go to the link on the screen, and so that you'll be able to do the survey and then get your certificate of attendance from EIT. All right. So I'll be posting it here as well on the chat. Okay, how to receive your certificate. Okay. All right. So yeah, yeah, thank you so much, Dr. Nasir. Thank you so much for sharing your expertise here, and thank you so much for the presentation. It was really informative, and I hope everyone was able to get the information that you need. And yep, thank you so much. So that's it for today, and hope to see you guys in the next webinars. Thank you so much, Dr. Nasir. Thank you so much again.
Thank you, everyone, and have a good day.
Have a good day.